Raw arithmetic data is inherently noisy, filled with high-frequency fluctuations at every local prime. To map this into a global coordinate system, we have to process those fluctuations systematically. The Adelic Langlands Program organizes this process into 4 stages. It starts at an innermost spectral engine and moves outward to a global, non-abelian architecture over the Adel ring. This pipeline shows the practical side of that architecture, the concrete mathematical path turning raw data into a stable geometric render. We focus on the transition from step 1 to step 2, calculating the buffering cost of that arithmetic noise using discrete matrix algebra. While the framework is designed to encompass the entire Adelic ring, its engine is built on these discrete, step-by-step matrix operations. This is the primary filtering tool, the Schur complement equation. It acts on a full interaction matrix A, representing unprojected spectral data. We define block D as the high-frequency degrees of freedom we eliminate, while block B represents our slower, coherent subspace. By isolating and projecting away the D block, we generate a cleaner residual state. This discrete spectral projection separates high-frequency internal noise from the coherent modes we need to track. This method only works if we can cleanly partition our matrix into these distinct subblocks. So why does this interaction matrix allow such a clean separation? The answer lies in equitable partitions. When vertices group perfectly, they satisfy the intertwining formula, AP equals PB. This combinatorial symmetry allows quotient matrix B to isolate global spectral information. Applying this, we peel away internal noise layer by layer, creating a Schur complement tower. Without this exact structural symmetry, the internal noise remains entangled with the global signal, which prevents the construction of the unique spectral projection required for the final field equations. Eliminating each block D in our tower isn't free. We have to mathematically measure the cost of resolving each layer. We use the p-adic valuation function to track this, looking at the determinant of each eliminated block D. This function counts how many times a prime number p divides that determinant. We sum these values across every layer to get the cumulative valuation, Vp. This total represents the liquid buffering cost, the exact amount of mathematical stabilization required before the data stream can be rendered as a field. Let's calculate a 5-vertex twin graph. We refine the graph over layers n, measuring the cost for prime p equals 2. At layer n equals 1, the determinant is -2. 2 divides this exactly once, making our cumulative valuation E1 equal to 1. At layer n equals 2, the determinant is -12. Since the highest power of 2 that divides 12 is 4, or 2 squared, the valuation E2 is 2. Now look at layer n equals 3. The determinant is -56. What is the 2-adic valuation here? Because 56 is 8 times 7, and 8 is 2 to the 3rd power, the highest power of 2 is 3, so E3 is 3. This gives us a computable sequence, En equals n. It shows that exactly one additional critical mode is added for every new layer of refinement. To find the long-term growth pattern of this cost, we fit our sequence to the Iwasawa invariance equation. We map our sequence of 1, 2, 3 up to n onto this general formula. Because growth is purely linear, lambda is 1. There is no exponential growth, so mu is 0. With no constant baseline, nu is also 0. These 3 numbers provide the arithmetic fingerprint of the entire tower, allowing us to predict the cost of noise at any level of refinement. We've calculated these costs prime by prime, but the Adelic Langlands program is about global consistency. How do these local costs fit together? This is the Adelic product formula. It is the final test for the entire system. When we take the product of all local buffering costs and multiply it by the continuous spectral data at infinity, the result must be 1. If that product equals 1, the local pieces of arithmetic data have achieved perfect harmony, creating a stable and unique global render. To recap, we start by organizing our arithmetic data into block matrices. We use Schur complements to systematically project away the internal noise. We track the p-adic valuation of those blocks to find the exact cost of that stabilization, and we fit that sequence to the Iwasawa equation to find our global invariants. This matrix algebra provides the verifiable arithmetic pathway that makes the Adelic Langlands framework computable.